This video is designed to go over complex numbers, a review I anticipate for most of you, and also working with waves in 3 dimensions to expand on what we did last time. So we're going to talk first about how we use complex numbers in both the Cartesian form and the polar form, and in particular I'll emphasize the polar form of complex numbers, and we'll look at finding the real and imaginary parts of the number. Then we'll talk about how to find speed, frequency, wavelength from a harmonic function of a wave, as we started last time. And we'll emphasize looking at spherical and cylindrical waves and plane waves in 3 dimensions and the 3-dimensional wave equation. So the complex plane is a great place. The complex plane plots relevant physical quantities or real quantities on the x-axis. That's things like displacement. If you were looking at the actual physical displacement of an object, it would be plotted on the x-axis. On the y-axis, we plot the imaginary quantities or the non-physical quantities such as phase. And the imaginary values are written or drawn as a displacement along the y-axis. So this is where our letter I, our symbol I, is used to define displacement along the y-axis. And yes, you'll know that I is in fact the square root of -1, which we'll get back to. So this is our basic complex plane with real values along the x-axis and imaginary values along the y-axis. We'll be drawing our vector z in the complex plane. So here we've got our complex plane again, and any vector z can be drawn in this complex plane. The magnitude of z is the red bar, and we can write this as x plus I, y. So it's like writing a vector where we would use the vector components x and y, except here we have the I in addition to tell us that we need to plot it along the y-axis. Now take a look and you'll see that the x variable is actually equal to r cosine theta, and the y variable is equal to r sine theta. So our complex number now has an x component and a y component, and we want to be able to use these components to define both the magnitude of the vector and the direction of the vector, or this angle theta, in our complex plane. If we start with our complex number z equals x plus I, y, we also will remember that the complex conjugate for a complex number is z star. And for the complex conjugate, we simply negate or invert any imaginary components. So in this case, it would be x minus I, y. And the magnitude of a complex number is actually defined as, we write it with those 2 bars, that z magnitude is defined as the square root of z times its complex conjugate. What you'll see if you multiply that out is that you have simply the square root of x squared plus y squared. And that's what you expected from looking at this picture of x and y, and this makes a right triangle. You would expect that x squared plus y squared should equal z squared, or the magnitude is the square root of x squared plus y squared. Now how about the angle? The direction of our vector, defined relative to the positive real axis, is the inverse tangent of y over x. Again, as you would expect from the angle as it's drawn here, and y over x, or the inverse tangent of y over x, giving us that angle. So this letter I, the symbol I that we use all the time, well, I is actually in the complex plane, I is a counterclockwise rotation of pi over 2, or 90 degrees. So let's look at an example. Suppose that b is along the x-axis, as it's drawn here in red. Well, if we multiply by I, so now we have our quantity I times b, look, now we have an imaginary number of length b that's along the imaginary axis. So we draw it as I've drawn it in the picture here. And what it is this vector b rotated by 90 degrees, rotated by pi over 2. And if you try this starting at any position, you'll see that what I does, multiplying by I, is it actually rotates your vector by 90 degrees. Kind of a fun little thing here. Just a couple of experiments or examples dealing with imaginary vectors and the complex numbers and the imaginary symbol I. So with anything where we have choices and I'm asking a question, what I expect you to do is to pause for a moment and come up with the answer, and then I will go ahead and show the answers. But you can pause the video here before seeing the answer. So which of these pictures represents I squared b in the complex plane? So you can pause here. And what you'll see is that I squared times b would be a rotation of b by 90 degrees. And then, in other words, b being just a positive value magnitude b, rotation by 90 degrees, rotation by 90 degrees again, and we get a line in this direction. Another way of thinking about this is looking at how do we write I squared b in this complex plane. So pause here. And yes, after you think about it, we see that I squared is simply minus 1. So it becomes minus b. And if you look back at this picture, minus b would be along the real axis in the minus b direction. All right, so a nice result of this is that I squared b now equals minus b, and I squared then equals minus 1, I equals square root of minus 1, and we knew all that already. Couple review questions. So the expression 1 over I is equivalent to which? Pause here. And you'll see that the expression 1 over I, this is a little bit of a tricky one, is equal to minus I. You can prove that to yourself by multiplying by I over I, and you will get minus I. What about the expression minus I over I? Pause. And you see that this is, in fact, minus 1. There is nothing particularly magical about that. It's simply minus 1. But you can prove it by multiplying by I over I, or just dividing through by I. Okay, so we're going to take a little segue here with that introduction to the polar and Cartesian form, to the polar form of complex numbers, and talk about Euler's theorem. And the way we get to Euler's theorem is actually by doing a Taylor series. I'm not going to do the Taylor series just as a little footnote, but I will show you how you would use it. So the Taylor series is defined like this. It's a function that's a series. And the Maclaurin series is a particular Taylor series expanded around a equals 0. So rather than expanding around a general a, you expand around a equals 0. And that looks like this, where your function now, instead of having a's in it, we put in zeros. Now, to get to Euler's theorem, what we do is we write the Maclaurin series for each of the following expressions: cosine theta, sine theta, and e to the I theta. So write all those out with terms up to as many terms as you want, and then compare them. And what you will find is that when you combine your real terms and you combine your imaginary terms, the real terms will all add to, you'll see that the real terms are cosine theta and the imaginary terms are sine theta, and when we add them together, we'll find the function that we had for e to the I theta, and this becomes Euler's theorem. You could try it sometime, write it out. If you didn't do it in a math class, it's kind of a fun exercise to see that it really works out. Trying to remove the cat here. Okay, so Euler's theorem. This is not really a joke. Euler's theorem is your best friend. E to the I theta equals cosine theta plus I sine theta. We will be using that all the time, going back and forth between the Cartesian plane and the complex plane, or polar form of our numbers. So a couple quick reviews of Euler's theorem. What's the value of e to the I pi over 2? Pause here. And you find that the answer is actually I. So e to the I pi over 2 is cosine pi over 2 plus I sine pi over 2. The only non-zero value there is sine pi over 2, and that gives us I. The next question, what's the value of e to the minus I pi over 2? And pause. And we find that it's minus I. You can draw these as well in the polar plane. This is, or in the complex plane. This is practice of using the complex plane. And how about e to the minus 2 pi I? Pause. So you'll see that 2 pi I, you'll find cosine theta plus I sine theta. We have cosine of 2 pi and I sine of 2 pi. Sine is 0, cosine is 1. This one's a little bit harder. Take a minute and write it out. See if you can find the correct answer. Pause here. And you will see when you work it out that you get minus 1/2 minus I root 3 over 2. So here's what we're going to get out of this. When we're dealing with the polar form, well, now we're introducing the polar form. What did you notice about those examples? In each case, the angle in the exponent, so e to the I theta, is the angle of the complex vector z. If you were to write your complex vector z as x plus iy, the angle would be the same as e to the I theta. And the magnitude of your complex vector is still r. In the examples we did above, the magnitude was simply 1 because we didn't multiply the e to the I theta by any other constant. So what this tells us is that we can take our complex number z and we can write it either in the Cartesian form that we had before, x plus iy, or we can write it as r, magnitude e to the I theta. We still have now x equals r cosine theta and y equals r sine theta, which we can see by using Euler's equation as well. So e to the I theta is cosine theta plus I sine theta, and x plus iy. We find that those expressions for x and y. So in summary, Euler's theorem is now e to the I theta equals cosine theta plus I sine theta. Just remember that if you're not real familiar with it, we'll keep using it and remember it. When we want to write our complex numbers in Cartesian form, we write z equals x plus iy. And the magnitude and direction are as defined previously. When we want to write our complex number in polar form, we have z equals r e to the I theta, with the angle defined as, and the magnitude as defined previously. And these numbers have real and imaginary components. The real component is simply x. The imaginary component is simply y. And you will see that the real component could also be written as z plus z star over 2, and the imaginary component is z minus z star over 2. All right, so that's our introduction to complex numbers. There is more. In fact, there's complex algebra. And what we've just discussed is essential, as is complex algebra. And what I'll ask you to do is review your text, pages 14 and 15, for the particular mathematical operations with complex numbers. Okay, so we're now going to move on to waves. And we're going to start by talking about the sinusoidal traveling wave that we began to discuss last time. And we'll look at its velocity, the units involved, and some of the relationships between k, omega, f, and c, and lambda. So let's start with this wave and discover what its velocity is, not by doing the derivatives but for the wave equation, but simply by looking at the expression. So the expression on the right, a sine 2 pi over lambda x minus vt, the velocity is simply v. And that's fine. If we can write anything as x minus constant times t, that constant is the velocity. But if we look at the expression on the left, we can write it as a sine k times x minus omega over k t. And that tells us that the velocity is now omega over k. That's a nice little, we'll be seeing this velocity equals omega over k several times. And returning again to this expression, let's look now at the different units and some relationships between lambda, k, omega, and f. So if we think about the definition of lambda, lambda is the wavelength of a wave, and it has units of length. In the SI units, that is in meters. It has dimensions of length, units of meters. So what does that make k? The expression above says that k must be the same thing as 2 pi over lambda, if we compare the two. And that means that the units of k are 1 over meters, or we'll say inverse meters. Now let's look at omega. So omega is the angular frequency, and omega is defined as 2 pi f. What that means is that the units of omega are radians per second or inverse seconds. We will know from context whether inverse seconds is angular frequency or frequency. Just a few more relationships between lambda, k, omega, f, and c. In a vacuum, the speed of a wave is c. Then we can express the speed as lambda times f, or omega over k, in a vacuum. Those are all vacuum values for lambda and for k. F and omega are fixed by the physical function of whatever it is that's making your wave. All right, so that will give you just a little more grounding in the variables and will help with the last problem on our homework assignment. Now we're going to do one last section here on the wave equation in 3 dimensions. So we've explored the wave equation in 1 dimension so far, and we've discussed that a function is a wave, it's a traveling wave, if it satisfies this expression, partial square root of psi as a function of x and t with respect to x squared equals 1 over v squared, partial square root of psi with respect to t squared. In 3 dimensions, we simply have the 3 different partial derivatives, and what that is a Laplacian, or del squared. So we have del squared psi equals 1 over v squared, partial squared psi with respect to t squared. And remember that del squared is partial squared with respect to x squared, plus partial squared with respect to z squared, plus partial squared with respect to, y, plus partial squared with respect to z squared. And that looks kind of messy, but it'll really be quite helpful. So when we're dealing with spherical and cylindrical coordinates, what we want to be able to do is use the wave equation in these coordinates, because it'll make it easier to work with waves that have spherical or cylindrical symmetry. For example, the most common is that a wave coming from a laser is actually not a plane wave, although we will make approximations, but waves from a laser are really spherical waves. So that's one place where we'll apply the spherical waves. Now, we get into more math. The Laplacian in spherical coordinates are theta and phi, as defined in the picture on the right. Is kind of messy. I'm not going to read all that. There's a lot of terms. There's a partial with respect to r, partial with respect to theta, partial squared with respect to phi squared, and it's, again, kind of messy. But if you have a spherically symmetric wave, then it'll actually work pretty simply. And that's because a spherically symmetric wave only has change in r. So we're going to look at a couple pictures here. A spherically symmetric wave. What does that mean? It means something like this, where you imagine that red dot as the source of the wave, and it emanates outward, the wave emanates outward in all directions. So the only thing that makes the wave change, that makes the value of the wave change, is the distance from that point source, r, and that's r. The angle theta, it's symmetric around any angle theta and also any angle phi. Another picture of a spherically symmetric wave, which also illustrates other principles, but this is saying if you've got a point source, like a candle, the waves will emanate in all directions and you'll have a spherical wave. So with that spherical symmetry, the derivatives with respect to theta and phi disappear, and we have this simpler form of the wave equation. And there's an example that's worked through on page 21 of your text, dealing with a spherical wave, a over r sine kr minus or plus omega t plus phi, and please go through that example. I'm not going to do that here because it's written out very clearly in the text. Now, cylindrical waves, we then go back to our full Laplacian and we say, well, if we're writing our Laplacian in cylindrical coordinates, in terms of rho, phi, and z, the Laplacian is as written here. Del squared equals, etc. So what does cylindrical symmetry mean? Cylindrical symmetry means that the only thing that makes the wave change is rho. Not z, not phi, but just the distance away from the z-axis. So let's do an example here. This is a problem from the text, but it's not assigned in homework. Psi of rho and t equals a over root rho e to the I k rho minus or plus omega t. That's the function that we're dealing with. It's a cylindrical wave. It depends only on rho. And as we just said, the only derivatives we need are those with respect to rho, so the Laplacian gets a bit simpler. We'll go through this two terms of the Laplacian and then put them together and see if our wave as defined here really is a wave, if it satisfies the wave equation. Let's start with the derivatives, taking the two derivatives, and then put it all together. So the derivative with respect to rho, take the partial with respect to rho of a over root rho e to the I k rho minus or plus omega t. We do this as a chain rule. First, a over square root of rho times the derivative of the second term, plus the derivative of the first term times the second term. So there's our chain rule written out, and our result here is ik times psi. Notice that if you look at this term, the first term in this function, a over square root of rho, e to the I, etc., is psi. So that's where that comes from. And in the second term, we see the same thing again. Square root of rho comes out of the rho to the 3/2, and we're left with rho times, or 1 over rho times 1 over square root of rho. All right, so that's our first derivative. We're going to use that first derivative now to take the second partial derivative. And when we do our second partial derivative, we're using the chain rule a couple of times. In each case, whenever we see that we're taking the partial derivative of psi, we'll plug in what we found for the partial derivative in the previous step. And the result we find, go through the steps here, see if your algebra matches mine. The result we find is minus k squared psi minus ik over rho psi plus 3 over 4 rho squared psi. Not terribly tidy. Now we're going to put it all together into the Laplacian. So adding it all together, we get what we see at the bottom here. Del squared psi equals, final form on the right, 1 over 4 rho squared psi minus k squared psi. Again, take time with that algebra if you'd like. The question we started asking is, does our function satisfy the wave equation? That's our initial function, and we want to see if when we plug it into the wave equation, it works out. So here we go. Del squared psi equals this expression, and 1 over v squared partial squared psi with respect to t squared equals minus or plus omega psi. Oh dear, that should be an omega squared. So these could be equal, but only in certain conditions. Only if our velocity equals omega over k. And you notice this little extra term here, 1 over 4 rho squared psi. There's no 1 over rho squared term over here. So we're going to have to justify why we can ignore that term. The way we justify it is we say, well, 1 over rho squared is probably small. And that would be true for any large rho. So we've determined that our function is a traveling wave. And this should be an omega squared here, not an omega. And that works out. Our function is, in fact, a traveling wave given the assumptions we said we need to make. So you'll do similar things for a spherical wave or a plane wave or any other three-dimensional wave. You can go through the steps, take the derivatives, and show that the wave satisfies the wave equation. All right, one last type of wave. Now we have a plane wave. A plane wave is one of the most common things that you'll see, even though it really doesn't exist much in nature. And a plane wave is one in which all of the phase fronts, or the crests of the wave, travel as a plane. So look at the picture on the left. We're drawing here the crests and the troughs of a wave and the associated electric field. We'll get into that next time. And we're imagining that this wave is not just a single photon, it's not just a single beam, but there's a whole line of them traveling in a plane that all the crests are matched up in a line. So this picture on the right shows this many sheets, many planes traveling towards in some direction here. The thing is, they don't simply travel along an axis as is drawn. Like, it's not always along the z-axis or the x-axis. We don't know what direction they're in, therefore it's a three-dimensional wave, even though it looks kind of simple. So in one dimension, we had psi of x and t is a sine kx minus omega t plus psi is a general form for a one-dimensional wave. And in 3 dimensions, we're going to introduce x, y, and z and t. And now what's changed is our k variable and our r, because those are the variables that are in space. So let's expand on that idea a little bit. The plane wave, as we've just written, in 3 dimensions is sine k dot r minus omega t plus phi. But the wave vector k and the position vector r are now vectors. And they have components, as vectors would, where k has an x component, kx I hat, plus ky j hat, plus kz k hat. And the r vector has 3 components as well in the I hat, j hat, and k hat direction. So whenever we deal with the direction of our wave, we need to consider the x, y, and z components of k and r. Remember, well, maybe you don't remember, but there was a reason to do all this, the Euler's equation. And one reason is that we will find that we'll go back and forth between the complex representation and the sine and cosine representation. So here we can write that wave as a e to the I k dot r minus omega t plus phi. And that is often just easier when you're dealing with taking derivatives and stuff. It's easier to take derivatives of an exponential than it is to do multiple derivatives of sines and cosines. Okay, so one of your problems in the homework, problem 1.20, is to determine the vector and other parts of the wave, but primarily the difficulty is determining the vector k based on the direction that the wave is traveling. And you can do that in problem 20. And that's it for our discussion of waves.